High above the cloud line, the Himalayas look perfectly still. It is a landscape defined by extreme geography and almost total isolation. But look down into this specific canyon. The river here makes a violent, unexpected U-turn around the mountain. This is a geographic anomaly called the Great Bend, and right beneath this exact spot, engineers are quietly building a $168 billion hydropower system. To generate enough electricity to reshape regional power grids, they are ignoring standard surface construction. Instead, they are hollowing out the rock itself. Until now, the most reliable way to extract massive clean energy from a river was straightforward. You build a massive concrete wall straight across it. China's Three Gorges Dam on the Yangtze River holds the current global record. It produces 22.5 gigawatts of electricity. A gigawatt equals 1 billion watts, meaning this single structure can outproduce dozens of nuclear power plants working simultaneously. But holding back a reservoir that stretches over 400 miles required forcing more than 1 million people to pack up their entire lives and relocate. Entire farming communities, river ecosystems, and centuries-old archaeological sites were permanently submerged. The sheer physical mass of all that stored water was so immense that geologists recorded it slightly nudging the Earth's crust, microscopically altering the ground beneath the reservoir. Surface megadams prove we can power whole nations with rivers, but the severe collateral damage to the surrounding environment forced engineers to seek a completely invisible alternative. Deep inside the Himalayas, buried so deep that satellites cannot see it, the environment becomes entirely claustrophobic as we descend. This schematic of the Great Bend illustrates a massive natural altitude drop. You can see the severe vertical difference between where the river enters the mountain curve and where it exits. Nature already built the drop. Rather than damming the river, engineers are boring tens of miles of straight tunnels straight through the mountain to short-circuit the water's natural path. Gravity pulls the captured water through these rock tunnels at terrifying speeds, slamming it into heavy turbines hidden inside deeply buried caverns. By treating the mountain itself as the machine's casing, this network is designed to generate up to 300 billion kilowatt-hours every single year. The engineering is precise, but the location is volatile. The Himalayas are an active, highly unstable geological zone. This diagram maps the primary threat. Beneath the project site, the massive Indian and Eurasian tectonic plates are colliding. This creates tectonic friction, a constant grinding of continental rock that triggers frequent earthquakes. That unpredictable geological pressure actively twists and squeezes the rock. The engineered tunnels physically warp and buckle inward under the stress. On a surface dam, inspectors can spot an exterior crack forming. Underground, water rushes through deformed tunnels under extreme pressure. A microscopic fissure hidden in the rock can instantly trigger a massive internal blowout. The engineers map every stress point they can find, but ultimately, they are forcing a rigid mathematical blueprint into one of the most chaotic geological battlegrounds on Earth. Back on the surface, the water captured at the Great Bend eventually flows out into vast, interconnected basins relied upon by millions. When that water reemerges from the turbines, it hasn't disappeared, but its crucial temperature, the heavy sediment it carries, and the exact timing of its seasonal flows are completely altered. Look at this map tracking the river's outward path. Those alterations cross international borders. Small changes at the mountain source cascade downstream, directly impacting soil stability, agriculture, and fish migrations for populations hundreds of miles away. Rivers run right past state lines. Capturing this much water underground forces downstream nations to participate in a massive ecological experiment they never consented to. If the tunnels hold, this establishes a new reality for global infrastructure. We can rely entirely on natural gravity and topography to replace fossil fuels, drawing immense power from the Earth without bulldozing its surface. But if the engineering fails, the river won't negotiate. The sheer pressure will rapidly flood and crush every tunnel and cavern carved into its path. We are watching a planetary laboratory at work. The ultimate test isn't whether we can build a machine inside a mountain. It's whether we fully understand the forces of the Earth before we try to rewrite them.